All right, so we're going to learn about Hess's Law today. So Hess's Law is one of the many ways that we can calculate the delta H for a reaction. And so how we calculate delta H depends on what we are given. So let's say you're given a series of equations along with their delta H's. Well, according to Hess's Law, if the sum of two equations, let's say, yields another equation, then the sum of their delta H's will equal the delta H for that equation. Or in the notes it says the enthalpy change, delta H, for a reaction is the sum of the enthalpy changes for a series of reactions that add up to the overall equation. So let's take a look on the example in number 7 on page 694, and I'll work that out with you. So consider this reaction. Now, something that should be pointed out is that we learned how to calculate delta H for a couple types of reactions already, those being synthesis and decomposition reactions, or formation and decomposition reactions. Well, what if it's not a formation or decomposition reaction? How do you calculate the delta H? So that's our goal. We're trying to find the delta H for this reaction. So here's what we're given. We're given a couple equations. So here's the first one. We're given thermochemical equations. And then the second one looks like this. And so our goal is to do this. Take these two equations. I'm going to number them just so we can keep track. So 1 and 2, these are the equations to be added. And so what we want to do is manipulate them in a certain way so that when we add them up, they're going to give us this equation. And according to Hess's law, if those equations can be added up to give us our original equation, then if we add up their delta H's, then we should get delta H for the original equation. So how do we do that? We can't just add them as is, because we'd have what, BaO plus 2SO3 plus H2O makes H2SO4 plus BaSO4. We want to end up with our original equation. So what we want to do is we want to compare the compounds, or compare all the substances, I suppose. Compare the substances in the equations to be added to the original equation. Do you notice anything? Is there anything that is in the equations to be added that is not in our original equation? Well, I see SO3 is nowhere in our original equation. And so what that means is SO3 needs to cancel. And so in order for it to cancel, it needs to be on opposite sides of the two equations to be added. So it's sometimes necessary to flip one or more of the equations, or to multiply one or more of the equations by some coefficient in order to end up with our main goal, that being the what I call original equation. All right, let's take a further look. So we need to get rid of SO3. That's one thing. Let's look at our original equation and see where each substance is in that equation and compare it to where it is in the equations to be added. Let's start with barium oxide. Barium oxide is on the left side of our original equation, and it is on the left side of the equations to be added. So that's on the correct side. So chances are we're going to leave that equation alone. Let's keep going. H2SO4 in our original equations on the left side, but in the equations to be added, it's on the right side. So that's not good. So chances are we're going to flip equation number 1. Let's keep going though. BaSO4, it's on the right side of our original equation. It's on the right side of equation 2. It's in the correct spot. That's good. And then H2O is on the right side in our original equation, left side of equation number 1. So it looks like we need to flip equation number 1. So let's take that equation and write it in reverse. So H2SO4 on the left, SO3 and H2O on the right. Now, make sure that if you take an equation and you flip it, that whatever equation you flipped, you cross off. So I'm going to just cross this off so I know that we're not going to use that anymore. Now, we talked about this with heats of formation the other day. If a reaction is, say, exothermic, then the reverse of that reaction will be endothermic. And that's exactly what we have here. The equation number 1 is exothermic. That reaction is exothermic. So the opposite of that, which we wrote here, must be endothermic. So once again, I'm going to cross this off because I want to make sure that I don't mistakenly use that. So now I'm going to add these two equations. Notice at SO3 we have one on the left, one on the right. That's great because those need to cancel. Let's bring everything down. And what we should end up with is the exact same equation as our original equation, this one here. If it's not exactly the same, then something happened, there's an error that occurred, and you need to fix that. So this is the work. But again, let's go back to the original question. The original question is, what is the delta H, the enthalpy of that reaction? And so in order to find that, we simply take our delta H's here and add them up, and we get our answer. So go ahead and pause the video and punch that up and see what you get. So it looks like this reaction is exothermic. We have a delta H of negative 135.2 kilojoules. All right, take a look at this example. So this time we have a series of 3 equations, and our goal is to find delta H for this reaction. So we need to take those 3 equations, manipulate them in such a way that when we add them up, we end up with this equation here. And then we're going to add up the delta H's and get the delta H for that reaction. Remember, if you flip an equation, you need to change the sign for delta H. If you multiply an equation by some number, then you need to do the same to the delta H. So again, this delta H here, this is per 1 mole of CO2. And this delta H here is per 1 mole of H2O. This is a heat of combustion. We talked about this the other day. That number there is per 1 mole of substance that is burning. Now, I introduced the term the other day, mole of reaction. So technically, these are all per mole of reaction. And we have 1 mole of carbon dioxide per mole of reaction, 1 mole of water per mole of reaction, and 1 mole of methane per mole of reaction. All right, go ahead and pause the video and set this up, and we'll compare answers. All right, so let me walk you through this a little bit. I've written some stuff out. So equation number 1 from the notes, take that and leave that as is. Equation number 2, take that equation and multiply it by 2. Why by 2? Well, if we look in equation number 3, we have 2 waters that need to cancel. And in equation number 2, we only have 1 water. So I want 2 waters here so that it will cancel. And because I'm multiplying that whole equation by 2, I must also multiply the delta H by 2. Equation number 3, I want CH4 on the right side. So I've taken that equation, turned it around, change it from negative 890.3 kilojoules to positive 890.3 kilojoules. All right, so let's see what happens. We have 1 CO2 on the right and 1 CO2 on the left. Those cancel. 2 H2Os on the right, 2 H2Os on the left. They cancel. I have 2 O2s on the left and 2 O2s on the right. So those are going to cancel. And I think that is it. So we have C plus 2H2 makes CH4. And what do you know? That looks exactly like the equation that we're trying to find the delta H for. So we know that our work is right. As long as you change the signs, multiplied your delta H's correctly, then delta H should be correct as well. So when we add all this up, we should get negative 74.8 kilojoules per mole. Notice something? What kind of equation is this? What kind of reaction? This is a formation reaction. We're forming methane from its elements in their standard states. And so technically this delta H here happens to be delta HF for methane. Now, if you want to confirm that this is in fact the delta HF for methane, you can take a look in the back of your book and you should see negative 74.8 kilojoules. All right, that concludes this lesson. Thanks for watching. Next time it'll be entropy.